Good morning and welcome back to day number 2 of geometry. Today we're going to be doing lesson 3.1.2. How I wanted to start the class period today, however, was doing a warm-up problem, recapping what we did yesterday. So on your notebook paper, you can do this warm-up for today. The date for today is going to be Tuesday, April 7th. What I'm going to ask you guys to do is to dilate this triangle by a zoom factor of 2. And so what that means is we're going to take it and we're going to dilate it about the origin, so just like we did yesterday. And then you're also going to dilate it by a zoom factor of 1/2. So on your paper you can draw this picture right here with these coordinates, and then do your best to try and dilate it by a factor of 2 and a factor of 1/2 and see what we come up with. We'll check back in a moment. Hopefully you guys got something that looks like this. The triangle I drew in red was stretched by a factor of 2, and again that was done by multiplying each of the vertices by 2. And so then the second one I did in blue is a zoom factor of 1/2, and so you notice that the triangle is smaller. It hasn't changed its orientation in terms of it hasn't rotated at all, but it is smaller by a factor of 1/2. And so hopefully you can see then that the triangles, when we are multiplying by a zoom factor, an enlargement factor, a scale factor, those are all meaning the same things. When we do that by a number greater than 1, we're making it larger. And we do it by a number less than 1, it's going to make the figure smaller. So today's topic, what we're going to be discussing is this idea of similarity. And so it says, so far you've studied figures that appear to have the exact same shape, but not necessarily the same size. So how can we know for sure that two figures have the exact same shape? It's not just enough to say, yeah, that looks like they're the exact same shape. So this example right here is something that we supposedly did in the last investigation, but we kind of glossed over. But what it asks us to do is it says, which side of triangle A prime, B prime, C prime, so the one that's enlarged, which side of that corresponds to CB? Well, CB is right here, and so the side length that corresponds to that would be the side length C prime, B prime. And likewise, if I were looking at this side length AB, I could say that A prime, B prime is the side length that corresponds to that one. So it says, what is the relationship of the corresponding sides? And this is something that we're going to get into with similarity. Hopefully you can notice that if I were to look at the length of CB right here, that length is 4. I could count up 1, 2, 3, 4 units. The length of C prime, B prime is 8. So to go from the side length CB to C prime, B prime, to go to the bigger one, I'm multiplying it by a factor of 2. And so I could see that that's the exact same thing happens here. Going from AB to A prime, B prime, I'm multiplying those dimensions by a factor of 2. And so there's this relationship going on with all of the related, or what we're going to say, corresponding side lengths. All corresponding side lengths are related by the same multiplication factor. And so we're going to notice that as we move on to some of these new problems or these new ideas involving similarity. In your notebook, however, now is something where I would pause this in a moment and write down this little section right here. This is the definition for what it means for two shapes to be similar. It says, when two figures are related by a series of transformations, they're called similar. Similar figures have the same shape, but not necessarily the same size. Similar figures can be created by multiplying each side length by the same number. This number is called the zoom factor. And I've also referenced it a couple other ways. You might hear it said the scale factor. That might be something else. Or the enlargement factor. Those would all be synonymous terms. Nonetheless, two figures are similar when they have the same shape but different size, and all of the side lengths are going to be multiplied by the same amount. And so in this example it says right here, what is the zoom factor used to enlarge the puppy shown at the right? Well, as I go from the original to the enlarged, clearly I can see that I am multiplying by 3. So I would say that the zoom factor for this particular picture would be 3. Alright, so now Casey has something in mind with you guys at the same time. This problem 3-13 deals with Casey, and she's bored out of her mind, probably like some of you are, because she wants to enlarge her favorite letter, C. It says your team is going to have to help her out. Each member of the team is going to choose a different zoom factor below and then graph it. And we're not going to do that. I'm not going to ask that you do something like that. But what I want you to recognize is that this length, the longest length here on side length C, is 1, 2, 3, 4, 5, 6, 7, 8 units long. So if I were to enlarge that by a factor of 2, the new side length would be 16 units long. And so if I had a zoom factor of 2 going for this bottom length again, instead of being 6 units long, it would now be 12 units long, and so forth. So this length, or this picture of C would get much larger, and so it would look something like that if I were obviously enlarging it by a factor larger than 1. But this problem right here, problem 3-14, is something to note. It says, what happened when the zoom factor was 1? And one thing to take note of is when the zoom factor is 1, what happens is that the shape stays the same. And so this is something worth taking down right now, that the shape stays the same whenever you are multiplying by a zoom factor of 1. And so that in essence mean that you're multiplying each of the side lengths, each individual side lengths by 1, thus you're not changing the value of anything. So when two side lengths or two figures are multiplied by a zoom factor of 1, that means they have the same shape and the same size. We don't call those shapes similar. We actually refer to them as being congruent to one another. So this would be another word that you would want to throw down in your notebook, which would be the word congruent. And congruent means same shape and exact same size. So in essence, this means that the shapes are similar with a zoom factor of 1. Let's see if I can get that down here. So in order for two shapes to be congruent, that means they're the exact same. So similar with a zoom factor of 1. And so it says compare the shapes below with tracing paper and determine which shapes are the same. What you're going to notice if you were to actually do that at home, or if we had tracing paper, you would notice that side length B is not congruent, or this one B is not congruent because all the other ones have the exact same dimensions. So yeah. Moving on now, talking a little bit more about similarity. We're going to be looking at problem 315. And so we are going to look at the ratios of side lengths within similar figures. And so this goes back to the letter C with Casey. And it says here on letter A that since the zoom factor multiplies each part of the original shape, then the ratio of the widths must equal the ratio of the lengths. And so it says Casey wanted to show that this happens. And so in essence what they're doing is they're saying, hey, this side length 18, that corresponds or is in the same spot as this side length 6. So if I were to take 18 divided by 6, well, I know that that's 3. That has to be the exact same ratio as taking this side length of 24, which corresponds to 8. And I know that 24 divided by 8, that's also equal to 3. And so that's important. We want to note that these two side lengths need to match up with one another in terms of comparing their widths and their heights. Those numbers need to be the exact same. So in letter B here, it says when looking at Casey's work, her brother wrote down 8 over 6 equals 24 over 18. Are his ratios in fact equal? Yes, they are equal. However, I don't want you to do what Casey's brother did here. I want you to be able to compare the ratios of these side lengths that are in the exact same spot. And so let's not worry about letter B, but rather we're going to look at letter C, and this is where we get some math involved now. It said she's decided to create an enlarged C for the door of her bedroom, and to fit that in, it needs to be 20 units tall. So if X is the width of this new C, write and solve an equation to find out how wide the C on Casey's door must be. So at this point, if you haven't written anything down, I would pause the video for a moment, and then what we're going to do is we're going to work through to figure out how do we determine this side length X. So in order to do that, what I'm going to do is I'm going to go back to like what I did before. I always try and compare the corresponding sides, or the side lengths that are in the same spot. So I know that 20 corresponds to the side length of 8 in the smaller letter C. And the way that I write this as a fraction, I say 20 corresponds to 8. I can write that as 20 over 8. That has to be the same ratio as taking the other length in the bigger C, which I know is x, and I divide that by the corresponding side length in the smaller letter C, which is 6. And I know that these ratios have to be equal because these letter C's are similar. And we stated up above that all of the ratios of the sides have to be the exact same. So what I have now is an equation, and I can use some cross multiplication in order to solve it. What I'm going to do is I'm going to multiply across the equal sign as such to get rid of the fractions. And when I do that, 20 times 6 is 120. And 8 times x is going to just equal 8x. And so now I can simply solve for x by dividing both sides by 8. And in doing so, when I do that, I'm going to get x all alone. I'm going to get that x is equal to 15. And so when we have missing side lengths, what we can indeed do is we can find them by setting up an equation using this thing right here. When we set up a proportion, as it's called, of equating two different side lengths, and we're going to practice that more here in the next problem. So this would be another problem that you're going to want to write down on your paper. If you haven't done so already, I'll give you a moment to do so. And it says, use your observations about ratios between similar figures. So we're dealing with two figures that are similar, meaning that they have all of the corresponding sides have the exact same zoom factor or scale factor. It says, assume one triangle has side lengths 6, 7, and 10, while another has side lengths 3, 4, and 5. I'm looking at letter A. Are these triangles similar? So this diagram, just so you know, right here has nothing to do with question A. And so I'm going to just answer question A to begin with. It says you have a triangle with side lengths 6, 7, and 10, and another with side lengths 3, 4, and 5. Are they similar? Well, if they are similar, all of the ratios of the corresponding sides need to be the exact same. And what I mean by that is if I take the shortest length divided of the smaller triangle divided by the shortest length of the bigger triangle, that has to be equal to the medium length of one triangle divided by the medium of the other, and the large or the longest side of the triangle divided by the longest side of the other triangle. And so if I were to throw in what I know, I have side length 6, and I'm going to divide that by the corresponding side here of 3. That ratio needs to be the same as taking 7 divided by 4. And I want to know, is that the exact same thing as well as taking 10 divided by 5? Well, in this case, I know that 6 divided by 3 is 2 and 10 divided by 5 is 2, but 7 divided by 4 is not 2, and therefore the ratio of all of the side lengths is not constant. So I'd say that these triangles are not similar. This is my weak attempt at spelling triangles. Triangles are not similar. If I can write it all. Because they do not have a constant scale factor. They don't have the zoom factor being the exact same between all of the corresponding sides. So all of those ratios would need to equal 2 in order for us to know that those two triangles are similar. Now, in question B, it says, if the pentagons at the right are similar, so we're saying, yeah, they are similar. We don't need to try and determine that. What are the values of x and y? Well, what I like to do, especially if I can color code, is I like to take the side length 8 and highlight which side length that corresponds with in the other triangle. And so I can say that 24 over 8 does not matter the order in which you set up your proportion. You can go small length on top if you desire. I always like writing the biggest side length on top, but as long as I do that, I know that I'm going to, from here on out, write the larger of the two side lengths on top of all of my fractions. And so I can say that 24 over 8, that has to be equal to another ratio, and I'm going to pick this side length 11, and that side length of 11 corresponds to x. X is the bigger of the two, so I'm going to put that on the numerator as I did in the first fraction. I know that this proportion has to be equal. And so what I'm going to do is I'm going to solve for x to begin with. I'm not going to set up another one including y right now because I just want to solve for one variable. And so what I'm going to do is I'm going to cross multiply both sides here, and then I'm going to try and solve for x like we did in a previous problem. Why don't you attempt that really quick and see what you come up with. Hopefully you got x equals 33. And if I were to plug in 33 back up here for x, you know that 33 divided by 11 is 3, as is 24 divided by 8. So that's another way that we could have gone about it. But I'm going to set up a proportion to solve for this last ratio as well. I know that 18 over y is going to be another proportion that I'm going to solve with. And hopefully maybe you can recognize this right now. I need 18 divided by y to equal 3. And the reason I know it's going to be 3 is because these two ratios equal 3. So off the top of your head, you might be able to reconcile that y is going to turn out to be 6. And I know that because 18 divided by 6 is 3, and the zoom factor of all of these sides needs to be 3. And if not, what we could do is we could set up another proportion like what we did in the previous problem, where I took 24 divided by 8, and I could set that equal to 18 over y. Those are all the sets of the corresponding sides, and then I would cross multiply and solve like I did beforehand. So the main point of what we were trying to get across today is summarized in the next slide, which is found here in the math notes portion, and it's talking about ratios of similarity and zoom factor. It says the term ratio was introduced in chapter 1, but ratios are very important when comparing two similar figures. A comparison of two quantities is what's called a ratio. And so specifically when we're looking at shapes more or less like these triangles down here, what we do is we write a ratio of side lengths. And so here's one of the hypotenuse of the smaller triangle, and the enlargement is 10. And we write that as a ratio of 6 over 10. We're saying 6 corresponds to 10. And so the ratio between any pair of corresponding sides in similar figures is called the ratio of similarity. So this right here is called the ratio of similarity. We did that in the previous problem. If you go to back, we did 24 divided by 8, and that was 3. And so this math notes goes on to say when a figure is enlarged or reduced, each side is multiplied or divided by the same number. Well, there's several names for this number, as I've highlighted already. This text will refer to this number as zoom factor. So they're going to call this thing right here, the 6 over 10, as the zoom factor. So to help figure this out, if the figure was enlarged or reduced, the zoom factor is written as a ratio of the new figure to the original. So they're always going to take the ratio, or the number on top is the new figure divided by the original one right here. Since this number is bigger than 1, I know that this is going to be an enlarged figure. So there's a lot of information in there. Hopefully you can work through it and apply it in your homework. I'll be available for office hours if you need it. Otherwise, take care, and we will talk soon.